And in today's class, we're going to step forward from discussing what I would now start calling the motion of point-like objects to what we're going to be calling the motion of rigid bodies. And so that's today's topic, and we'll be continuing with this topic for several lectures. So let me just put it in perspective. When we talked about physics problems in the past, let me think of some great physics problems. There's, you know, the crate sliding down the incline. There's the bucket on a string on a pulley. There's the block on the spring, stretching the spring. When we analyze those problems, when we discuss those problems, we actually imagined as if the crate was a point-like crate. The bucket was a point-like bucket. The block was a point-like bucket, meaning that we imagine that the forces acting on the crate or the bucket or the block were all acting at a single point. And we could treat the crate, the block, the bucket as a single point. And of course, the crate and the bucket and the block aren't a single point. And the crate and the bucket and the block are really distributions of matter, distributions of mass. And so we're moving on in today's class to actually treat the size, the shape, the matter distribution of real life objects more realistically. So over the next classes, I'm going to tell you how we describe distributions of matter, like the crate or the block or the bucket, how we describe them in terms of what we call the center of mass, and how we describe them in terms of what we call the moment of inertia. And then we'll look at the motion of rigid bodies, like the crate and the bucket and the block. And we'll talk about the role of torques in the motion of rigid bodies. We'll talk about the Newton's laws of rigid body motion, and we'll talk about rotational energy, angular momentum of rigid bodies. So we're going to cover all those topics over the next handful of classes, next few classes. Today's class, we're going to sort of open up this world of rigid bodies by talking about rotational equilibrium. So this is a nice picture, I think. It's this giant rock on the top of this mountain. And that rock is just sitting there, balanced on, I mean, it looks precariously on some small amount of the mountain below it. And that's an example of, it's a dramatic example of rotational equilibrium, dramatic example of equilibrium overall. The rock is at rest, staying at rest, and it's therefore in equilibrium. It's actually in translational and rotational equilibrium. And we're going to explore this topic of rotational equilibrium and equilibrium in general as our introduction to the motion of rigid bodies. And specifically in today's class, I want to talk about a few topics I've listed here. Let me get my pen going. I want to talk about torques, which are really important ingredients in understanding rigid body motion. I want to talk about one of those quantities that we use to describe rigid bodies, center of mass. It's an important quantity in describing rigid body motion. And then we'll be talking about this idea of rotational equilibrium as an example of rigid body dynamics. And in each of these cases, I'm going to introduce the concept of torque and center of mass. I'm going to give you definitions of torque and center of mass. I'm going to write down some equations for torque and center of mass, and we're going to look at some illustrations, some examples. So that's the basic plan. Okay, so let's begin with torques. Torques are new to us, but they're related to something that's old for us. They're related to forces. So we're going to look at the relationship between torques and forces. That's our first topic here. So just as a reminder, that'll help us put torques in perspective, here's a reminder of forces. As you recall, forces are kind of pushes and pulls. And forces have size, magnitude. So you could have a large force, you can have a small force, you can have a medium-sized force. Forces have directions, they have orientations. A force could be up or down or whatever. And forces were keys to understanding what we now call translational motion. Torques are kind of twists or turns. So if you get something turning, like the ice skater there, or you get something turning like the winds in a tornado, there's torques acting that twists or turns that generate that rotational motion. So torques are twists and turns that play the same role as forces, i.e. pushes and pulls, for rotational motion as forces did in translational motion. Likewise, torques have a size or a magnitude. So you could have a small torque, you could have a large torque, you could have a medium-sized torque. They have directions too. And for example, you might have a torque that turns something clockwise, or you might have a torque that turns something counterclockwise. So there's a direction too. So forces, key in understanding translational motion. Torques, key in understanding rotational motion. Now, I want to describe the relationship between torques and forces, because actually torques are generated by forces. Torques are produced by forces. And so there's a clear-cut relationship between torques and forces. I think I'm going to show you a demonstration first. And that means I'm going to share a different screen. And it's a demonstration of, I thought I'd demonstrate to you how to open a door. That'd be a useful thing, be able to get in and out of the building when it's open again. And this is going to be how to open a door. Okay, so I hope you can see the door I'm going to open. It's not a real door, it's a little door. A small dog could use this door, but we couldn't use this door, couldn't get through that door. And I'm going to open this door. And if you notice, in my hand is a device that measures the force that I need to open the door. And so I'm going to measure the force that I need to open the door. And actually, right now, I'm going to open the door by pulling on this left-hand edge. I hope you can see my mouse, of the door, which is where the door handle is, because the hinges are over here on the right-hand edge. And then I'm going to open the door by pulling on the middle of the door. I don't normally do that. And then I'm going to try and open the door by pulling right over here on the far right, near the hinges. And we certainly don't normally do that. And we're going to compare the forces by comparing the reading on this force meter that I need to open the door at these 3 different locations, which are 3 different distances from the axis of rotation of the door. Think of the hinges, this vertical line with the hinges, as the axis of rotation of the door. And so over here on the left, I'm a long way from that axis of rotation. In the middle, I'm sort of an intermediate distance from the axis of rotation. And over here on the right, I'm very close to the axis of rotation. And so here I am opening the door when I'm a long way from the axis of rotation. There was nobody home. And you might notice that the needle on the force meter barely moves. It was about 0 and it stayed about 0. I remember doing this. It was so easy for me to open the door that it required almost no force. Now I'm going to try and do it at the middle of the door. And now you see I'm having to use a significant force. It's now reading about 1.5 newtons. 1.5 to 2 newtons, or even maybe even more, when I open the door in the middle of the door. Now I'm going to open the door, try and open the door by the hinge. So you notice something, I've stopped the video for just a moment. The first time I tried to do this, I just pulled the door over. It was so hard to open it. So you notice now I'm using 2 hands. One is holding the door frame because I'm going to have to pull hard. And you might watch the meter, it went all the way around and went back past 0. And so that's really 26 on that force meter. Again, the door's going all over the place. It's very hard for me. I was barely strong enough to open that door by pulling there. Okay, so let me go back to my slides. If I can remember how to do that. And what we just learned was that it was easy to open the door at the door handle. It was very hard to open the door close to the hinges. And it was sort of intermediately difficult to open the door by pulling midway on the door between the hinges and the door handle. I was opening the door by using a force to produce a torque. That force I was exerting was creating a torque. Now, to open the door required a certain torque. But to get that torque, I only needed a little force if I applied the force at a large distance from the hinges. I needed a much bigger force if I applied the force close to the hinges. So torques are created, produced, manufactured by forces, but not only does the force count, but also where you apply the force counts. If I applied at the door handle, it was easy to create the torque. If I applied it near the hinges, it's very difficult to create the torque. Now, I didn't show you this, but I could have shown you this. I mean, the truth is I forgot to do this part of the video yesterday. And so I got a little diagram of it instead of actually doing it and showing you with the pretend door. So this is a helicopter view of the door. Here on the left now are the hinges of the door. Here on the right is the door handle. And I'm going to apply this time always the force at the door handle, but in different directions. So you might want to try this out at home, for example. It's a nice experiment to try at home. It's easy. If I push perpendicular to the plane of the door, it's easy to open a door, close a door. If I pull in a direction that's away from the hinge, like this arrow here, or towards the hinge, then it's impossible to open the door. And if you do something in between, like this force here, it's neither applied perpendicular to the face of the door or parallel to the face of the door. It's at some angle with respect to the face of the door. It's sort of intermediately difficult to open the door. So this demonstration tells you that not only where you apply the force counts in creating a torque, but also the direction of the force counts in creating or producing a torque. Okay. Well, we can turn all that, all those experiments into an equation for a torque created by a force. And that's what I've done on this overhead. I need to get the pen going again. It'll just take me 10 minutes, I guess. So this is the definition of torque. The F in the equation on the right-hand side, that's the force I'm applying. The R, that's the distance that the force is applied from the axis of rotation. You see it depicted on the pictures here. And the theta, that's the angle between the force vector and this displacement vector r. It's the angle between the vector F and the vector r. So, for example, that angle between the two is 90 degrees in the upper case. That angle between the two is 0 degrees in the middle case. And that angle between the two is theta in this lowest case here. And so this is the recipe, really, for how forces make torques. And as I say, forces are the creators of changes in translational motion. Torques are the same things in the world of rotational motion. And this is how we make a torque out of a force. So, you know, this example A, where we open the door in the normal manner by applying a push or a pull perpendicular to the face of the door. Here the force and the displacement vector are right angles to one another, and the sine of 90 degrees, that's 1. So you get a maximum sized torque for a given force. Here, in the second example, B, that's not how you open a door. And in this case, the force and the torque, the force and the displacement vector are in the same direction. And that gives you 0 degrees between the force and the displacement vector, and the sine of 0 degrees is 0. So that's certainly not how to create a torque to open the door. And then this case at the bottom, C, that's somewhere in between, right? You're not going to get the maximum force of RF. You're not going to get the minimum force of 0. You're going to get a force that's determined by sine of theta. And so if theta is between 0 and 90 degrees, sine of theta is somewhere between 0 and 1. And so that's torques and how they're connected, how they're related to forces. The equation for the torque is sometimes written in a little different way, and I wanted to show you this little different way of writing it. It's in terms of what we call a lever arm. And it's easiest to see the lever arm on this picture. This is one of the cases from the last slide. And in this one, the force is neither perpendicular to the door nor parallel to the door. It's at this angle theta to the door. So from this direction of the displacement vector to where the force is applied, and this direction or line along the force vector here, you can make a right angle triangle. And here it is. Just turn those two lines into a right angle triangle that runs from the axis of rotation to this line that ran along the direction in which the force is acting. And the length of that line, that's called the lever arm. And, you know, this is theta, and this side of the triangle is R. So this line is the opposite side of the triangle. It's R sine theta. And that's what we call the lever arm. And so sometimes you'll see the the torque written in terms of the force, the distance of the force from the axis of rotation and this angle. Well, sometimes you'll see it just written as the force times the lever arm. And it's just another way of writing torque that's sometimes convenient. Sometimes you'll use one version, sometimes you use another version. And it just comes about from this little bit of geometry of this right angle triangle. Okay, let's look at an example calculating a torque. I got my bike out. I've been in the basement for 20 years, got it out, and I'm gonna try riding my bike. And I'm gonna try riding my bike by exerting a force on the pedals of the bike that will create a torque on the pedals of the bike, turning them, and that will propel me down the street, hopefully. So here's the information we're given. The length of the pedal arm is shown here in red. That's 0.15 meters, so 15 centimeters. I'm capable, apparently, of applying a 111 Newton force to the pedal with my foot. So that's the force here. Here's the force, strength. Here's the distance the force is applied from the axis of rotation. And then we're going to consider three positions of the pedal arm. One where it's 30 degrees away from the vertical, one where it's 90 degrees away from the vertical. That's what's pictured here. And one where it's 180 degrees away from the vertical, away from vertically upwards. And we're going to calculate the torque in these three examples. So this is an example of our equations for the torque. So on this slide, I'm solving two of those cases. So let's see. Over here on the left-hand side, I'm going to calculate the torque for this case when the pedal arm is 30 degrees from the vertical. This is a picture of it. That's 30 degrees. And in the second case, this one over here, I'm going to calculate the torque when the pedal arm is 90 degrees from the vertical. That's this case here. That's 90 degrees. So we'll do these two examples. Okay, so I, of course, always do this, make a sketch. In this case, we're going to make a sketch of the forces and where the forces are acting, and then we'll turn that sketch into an equation for the torque. So here's the axis of rotation. In green here, here's the displacement vector representing where the force is applied. So the force is applied at this point here. And then in blue, that is the downwards force of 111 newtons. And so that's a picture of the geometry here. And importantly, right, what counts is the direction between the vector r and the vector f. And that's this angle here. And that's 150 degrees from the geometry here. And so that's the angle theta that will go into calculating the torque. Okay, so here's the equation for the torque. I plug in the distance from the axis of rotation to where the force is applied. That's 15 centimeters. I plug in the strength of the force. That's 111 newtons. And then the directional information goes in by plugging in the sine of theta. And theta here was 150 degrees. And then I carry out that calculation. I'm just mentioning here that this piece here is actually the lever arm. That actually is not, because, sorry, this 0.152 meters times sine 150 should be the lever arm. Anyway, multiply these three things together. and you get this torque. It's 8.4 newtons meters. Newton meters are the units of torque because it's a force times a distance. And so that was the torque in that situation. On the right, I did exactly the same calculation, but for this new geometry. So, there's no difference in the distance from the axis of rotation to where the force is applied. There's no distance in the strength of the force. But now the pedal is at a different location with respect to the vertical. There's a different angle between the direction of R and the direction of F. It's now 90 degrees between those two vectors. And so the only thing that changed in my calculation on the left and my calculation on the right is the angle. The forces are the same strength. The distances from the axis of rotation are the same distances. But the angles with respect to the vector R and the vector F are different. And so this time I got 16.9 Newton meters torque. So this geometry, just like opening the door, that gives you the greatest torque. This one gave us a lesser torque. Here's the calculation for the last case, which was when there was the force exerted at 180 degrees to the vertical. So this force is downwards now. That's this pedal is downwards now. That's 180 degrees to the vertical. And in that geometry, right, the angle between, I always do that at least 10 times a class. The angle between the displacement vector R and the force vector F, they're now 0 degrees. And well, you probably don't need me to go through this calculation, but if I was then to calculate the torque, although the distance of the force from the axis of rotation is non-zero, although the force itself is non-zero, when I plug in 0 degrees, sine of 0 degrees is 0. And so this geometry gives you no torque whatsoever. You can't turn the pedals of the bicycle in this geometry, where the pedal arm is straight downwards and your force is straight downwards. You couldn't actually turn it in the other geometry that's kind of like that, where the pedal arm is straight upwards and your force is straight downwards. The best way to turn that, so if you're a champion cyclist, I'm not a champion cyclist, but I do know that the best way to apply your force is when the pedal arms are horizontal to the ground. That is, your downwards force is perpendicular to those pedal arms. Okay, second example. And this is an example I wanted to show because it's got a little trap in it, or a little minefield in it, that might cause you to put in the wrong angles for calculating the torque. So this is the reason for showing this one. It says, calculate the net torque about the center of a merry-go-round for when two forces are applied. There's a force, we called it F1, that's 1200 newtons. And there's a force, we called it F2, that's 1400 newtons. And they're applied on the edge, tangent to the edge of a merry-go-round. And the radius of the merry-go-round is 2.5 meters. So this is a sketch of that arrangement. So this is a helicopter view. We're looking down from above on the merry-go-round. And here's the axis of rotation of the merry-go-round at the center. And you see this force here, F1, it's being applied at the radius of the merry-go-round. And this force F2 here, it's also being applied at the radius of the merry-go-round. And now we've got two forces. They're going to create two individual torques, and we're actually going to sum them up to create the net torque, total torque, resulting torque. So let's go ahead and do that. And so here's my calculation. And so this single slide has the entire problem worked out for us. And basically, what I'm going to do on this slide is calculate the net torque by it's really the vector sum of the two individual torques, tau1, tau2, that are created by two individual forces, F1, F2. So we're going to do that. And I just reproduce the drawing, the sketch here. Okay, so this is the basic idea. Well, you'll notice I put in some signs there. So I noticed just from the drawing, right, that the force on the left, just think about that. Supposing you were exerting that force on the left, it would tend to turn the merry-go-round counterclockwise. So that force is kind of doing this. I don't know whether this works on video or not. The force on the right, on the other hand, F2, that's trying to turn the merry-go-round the opposite direction. So it's trying to turn it clockwise. And so I've chosen to call counterclockwise the positive direction and clockwise, therefore, the negative direction. And I've tried to indicate the directions of these two torques with these plus and minus signs. And so then I've just got to fill in the magnitudes. And so in the second line here, I filled in the magnitude of the torque that's created by force number 1 and the torque that's created by force number 2. So in both cases, they're the product of the distance from the axis of rotation, center here, to where the force is applied. So that distance is the radius of the merry-go-round. So that's true in both cases. Times the strength of the force. So F1 is the strength of the force on the left, F2 is the strength of the force on the right, times the sine of the angle between that displacement vectors R and those forces F1, F2. Now, here's the potential trap. Whoever wrote this problem down, it wasn't me, indicated that the position of the force on the left is at 30 degrees above the horizontal, and the position of the force on the right is at 45 degrees above the horizontal. But actually, that's just a trick. That's actually irrelevant. What counts is the angle between R and F, between R and F. And the angle between R and F in these two cases is 90 degrees. So whoever wrote this problem was up to some mischief, wanting you to plug in like a 30 degrees and a 45 degrees. But actually, we're just plugging in 90 degrees, the direction between the force vector and the displacement vector. So that's why I've got 90 here on the left, 90 here on the right. Okay, so at that point, I can plug in all the numbers, the radius of the merry-go-rounds, the sizes of the forces, and the sines of 90 degrees. And hey presto, here's the answer. It's 3,000 Newton meters for the force on the left, minus 3,500 Newton meters for the force on the right. So the torque from the force on the left is slightly smaller. The torque from the force on the right is slightly bigger. And so the net torque, they mostly cancel out, but the net torque is in a clockwise direction, in what we call the negative direction. Okay, let's move on. Okay, I think we're just about done with the quiz. So this quiz was about that relationship between forces and torques, how forces generate torques. In this quiz, we have these three forces, FA, FB, FC, acting on this object. Now, we're told all the forces have the same strength. They're all located at the same distance from the axis of rotation. But what's different is actually, the key thing that's different is that the angle between the force and the vector from the axis of rotation is different in these different, for these three different forces. So for example, for FA, R and FA are at 180 degrees to one another. For FB, R and FB at 90 degrees to one another. And for FC, R and FC are in the same direction. So this was 0 degrees, this is 180 degrees, this is 90 degrees. The 0 degrees situation, the 180 degrees situation, sine of 0 or sine of 180 gives you 0. Those forces create no torques. It's only the situation with the 90 degrees here that you get a torque, where sine of 90 degrees is 1. And so the correct answer to this one is that FB creates the largest torque. Okay. I'm going to skip this problem because it's a third example of torque, and I'll post it. I normally post for each lecture a worked out problem in modules as well. So I'll, over the next day or two, I'll post this one there if you're interested. But for now, I'm just going to skip it. So we can get on to our second topic, center of mass. The center of mass is important. So every rigid body, so the crate, the bucket, what else? The block, or you and I, we're rigid bodies too, from a physics perspective. We all have a center of mass. It's sort of kind of like, in loose words, it's like an average location of our mass. And the importance of the center of mass is the following. If you have a rigid body, right, and it's a distribution of matter, it's a distribution of mass, then gravity is actually pulling every little bit or piece of matter, every little bit of piece of mass in that body. So where do you say that gravity acts? It's acting everywhere over the body. It's acting throughout the body. The center of mass is the average point, sort of average point of where gravity acts. It's where we can imagine in a calculation. It's where we can think of in a calculation that gravity is acting. So in future problems, when we're dealing with objects that are distributions of mass, we'll think of gravity being acting at their center of mass. And we never did that before for the crate on the incline, or the bucket on the pulley, or the block on the spring. We avoided that question of where is gravity acting. Now we're answering it with it's acting at the center of the mass. So this is an important topic, and it gets us closer to real life, everyday situations. Okay, so here's, this is a diver, because I hope it's a diver. It looks like a diver getting ready to dive. And plotted on the diver is the diver's center of mass. So the diver is walking up, here's the diving board, I guess. Yeah, this must be the, oh, sorry. I'm assuming this is the diving board. I mean, the reason this is a picture of a diver is if you're a diver and you're going to do some tremendous somersault with, you know, 10 turns into the water below you. Your center of mass is a really important point. And all divers understand about their center of mass when they're doing their dive. Because during their dive, they can't change their center of mass. They can just turn and rotate about their center of mass. So this is why it's an example of a diver. And we're watching the diver's center of mass. Here's the diver just standing straight up. And the center of mass, sort of the average position of the diver's mass, it's somewhere here. I put my arms in the air, right? I've increased the average height of my mass. And so my center of mass has gone up. Then I lean forward. I'm not going to do this. I'll hit my head. Lean forward to do the dive. And my center of mass has both fallen downwards and it's moved towards the right because my mass has, some of my mass has headed towards the floor and some of my mass has headed towards the right. There's an interesting point here. An object's center of mass doesn't have to be physically in the object itself. In the first two cases, the object's center of mass, the diver's, was inside the diver somewhere. But in the third case, it's actually outside the diver. That's where the center of mass is. Okay, so in some cases, we can actually calculate numerically the center of mass. And here's a good example. So I've imagined some arrangement of point masses. And in this example, there's just 3 of them. There's this ivory one on the left, this blue one in the middle, this ivory one on the right. And they're arranged on this plane, this XY plane. And at certain coordinates. Each of them is at certain coordinates on the XY plane. The center of mass for this arrangement is the XY coordinates of the center of mass of the point mass assembly. And the X coordinate is determined by this little equation here. And the Y coordinate is determined by this little equation here. These are summations. These sigmas, I've not joined a sorority, don't worry. These sigmas are summations of, in the numerators, the products of the masses and their X coordinates, or the masses and their Y coordinates. And in the denominators, simply, this is just the sum of the mass of the entire arrangement. And so you could imagine, you know, this sum, this calculation of X center of mass, Y center of mass, if you've got 2 masses, 3 masses, 4 masses, and so on. It's just a numerical algorithm to find the average location of the mass. And it would be the location at which you would imagine that gravity would act on this arrangement, this distribution of matter. And so let's actually see if we can calculate for this arrangement of these 3 masses, where we know the masses and we know their locations, we know their XY coordinates, what its center of mass is. Let's see if we can do that. And so I'm going to calculate X center of mass, oops. I'm going to calculate this X center mass, Y center mass for this particular arrangement. So important point here is I know the values of each of the 3 masses, 5, 2, and 4 kilograms. I know the X coordinates of the 3 masses, minus 0.5, 0, and 1 meters respectively. And I know the Y coordinates. They're all actually located at Y equals 0. And so I've got enough information to figure out the center of mass. So let's do that. And so here's my calculation. Again, I drew it out and I made sure that I knew, right, this is M1. I'm going to call this one on the left M1. And here's its XY coordinates, minus 0.5, 0 meters. That's the XY coordinates of mass number 1. Here's mass number 2, blue mass, the one in the middle. The XY coordinates of this are just 0, 0. And here's the XY coordinates of mass number 3, the one on the right. 1, 0 in meters are the XY coordinates. So I know their masses, 5, 2, 4 kilograms, and I know their XY coordinates. And so I just have to apply this equation, where in the numerator, I sum up the products of the masses times the X coordinates, or the products of the masses times the Y coordinates. And in the denominators, I just sum up the masses. And so given I've got 3 masses here, I get 3 terms in the numerator, M1, X1, M2, X2, M3, X3. The same for the Ys. And again, I've got 3 masses, so in the denominator, I've just got M1 plus M2 plus M3. It's just a simple calculation like that. And it's, it's a little bit annoying, right, to have to multiply and add all these different numbers, but it's not a complicated calculation. It's just a simple procedure, simple algorithm for calculating this sort of magic point, the center of mass, where the action of gravity takes place. And so I did that. The total mass is 11 kilograms. So that would be in the denominator of both of these calculations. In the numerator, there's sometimes terms that are negative, some terms that are positive, and one term here that's 0. This was negative, this was 0, this was positive. When I added them up, I got a net positive number. And so my X coordinate of center of mass is about 14 centimeters. This was 1 meter here. This is half a meter here. 14 centimeters is somewhere in here. So I marked the location of the center of mass. Also, interestingly, there wasn't much of a calculation to do for the Y coordinate of the center of mass. Each of the individual masses were at Y equals 0. Therefore, the center of mass must also be at Y equals 0. And so here's the Y coordinate, the center of mass. That's exactly this point here. Okay, so I hope that helps. A few more remarks about center of masses. Sometimes you don't have a collection of point masses where you can apply that formula. But rather, you've got some symmetric, nice geometric distribution of mass. So a cube would be an example. A sphere would be an example. A cylinder would be another example. If that cube is a uniform distribution of matter, if that sphere is a uniform distribution of matter, if that cylinder is a uniform distribution of matter, then the center of mass is at the center, the geometric center of that cube or sphere or cylinder. And so when you have a nice symmetric distribution of matter, you don't really need a calculation. For this sphere here, because it's spherically symmetric, the center of mass is at its center of geometry. And likewise for the cylinder here, its center of mass is the center of its geometry. For the cube here, its center of mass is at the center of its geometry. And so that's sometimes another way that you can figure the center of mass of an object, because it has this sort of simple geometry, this symmetric geometry. Okay, here's a second example of calculating center of mass. So in this problem, I've got, I'm building a deck. Not that I could, but I'm building a deck and I've got a sheet of plywood here. And it's an L-shaped sheet of plywood. It's 8 foot wide. It's 4 foot tall, but it's got a hole cut out that's actually it's 4 foot by 2 foot. I've got that wrong. Where's the eraser? This is 4 foot. This is 2 foot. So this piece has been removed. And the question is, what is the center of mass of that arrangement? And actually, there's several ways you can calculate this. I'd love to go through showing you all the ways you could calculate this, but it would take too long and it would be presumably way too boring. But I'll show you at least one way you can calculate the center mass of this arrangement. And actually, it's a way that combines the two ways we've looked at so far: center mass of symmetric objects and center mass of point mass distributions. So let's see how that's going to work. Okay, so the first thing I did was actually divide that not very symmetric L shape into two parts that have a nice rectangular symmetry to them. So there's this red piece over here on the left, there's this magenta piece over here on the right. And the red piece on the left is 4 foot by 4 foot. Doesn't look like it from the scale of the drawing, but that's the sizes we were given. So this piece is now 4 foot by 4 foot, and this piece over here is 4 foot by 2 foot high. Now those squares, or those rectangles, their center of masses is, their center of mass is, because they're symmetric, is right at their geometrical centers here and here. So the first thing I did was say, well, look, I'm not going to think of this horrible L-shaped piece of plywood. I'm going to think of it as two pieces of plywood, a nice symmetric rectangle on the left and symmetric rectangle on the right. The mass of the one on the left is going to be twice the mass on the one on the right. I called the mass of the one on the left M1. I called the mass of the one on the right M2. And the one on the left is twice as big and so twice as massive. So I called their masses M1 and M2, but I know one of them's 2M, whatever M is, and the other one's just M. I also know the positions of their center of masses. So for the mass on the left, I called its center of mass position X1, Y1. It's halfway across here, so that's 2 foot. Halfway up here, that's 2 foot. So it's 2, 2 in feet. And for this one over here on the right, it's halfway across here, which is going to be 4 plus 2, that's 6 foot. And halfway up here, that's going to be 1. So this is 6 and this is 1. And so we now got distilled the problem, right? This is great, without doing any calculations really. I've distilled the problem of the L-shaped block of plywood into two masses, 2 point masses, where I know their relative masses, 2M and M, and I know the locations of the centers of mass. And at that point, I can then just apply those equations we met for the center of mass of collections of point-like masses. In this case, I've just got 2 masses. And that's what I'm actually doing on this slide here. So down here I'm calculating the x-coordinate center of mass and the y-coordinate center of mass, based on a mass distribution that is just these 2 masses, M1 and M2. And so if you remember those formulas, in the numerator, you multiply the mass times its x-coordinate. In the numerator for the y center mass, mass times the y-coordinate. And then in the denominators, you just add up all the masses. So for this particular case, it's easy. In the denominators, right, I've just got the 2m on the left plus the m on the right. That's going to be a 3m. In the numerators, I got 2m times x1 plus m times x2, or 2m y1 plus m y2 in the numerator of the y coordinate. And the nice thing that's going to happen here, you can see, in terms of calculating the center of mass, all these masses in the numerators and denominators, all the m's cancel out. All that was needed was that the mass was distributed evenly over the L-shaped plywood to calculate the center of mass. Once I knew that the left-hand piece had twice the mass, the right-hand piece had half the masses cancel out. And all I've got in my equations here ultimately will just be distances. The masses cancel out. Well, if you do the sum, I won't go through all the sum. Here's the 2 bits I'm adding together for the x coordinate center of mass, 2 bits I'm adding together for the y coordinate center of mass. I add them up, I divide by 3 m's in both cases, and I get a position for the center of mass. It says it's 3.3 feet in the x direction. So this is going to be, let's see, this is 4 feet here at this boundary. So it's going to be somewhere around here. And it's going to be 1.7 feet up. So this is 2 feet up. It's going to be somewhere here, which sort of makes sense. It's somewhere between M1 and M2. It's on that line between M1 and M2. It's closer. It's twice as close to M1, twice as far from M2, because M1 was twice the mass and M2 was half the mass. So our calculation makes perfect sense. Here's the center of mass. Okay, so last topic I want to look at is the equilibrium of rigid bodies. This takes us back to, remember the very first slide almost with the picture of the rock on the top of the mountain, and it was at rest, and it was staying at rest. It's in equilibrium. It's in translational and rotational equilibrium. Now I want to go back to that topic of translational rotational equilibrium of rigid bodies like that rock. That rock that's at rest and staying at rest is in equilibrium, rotational translational equilibrium, which in terms of equations means the following things. If you were to add the forces on that rock up, and there are forces from gravity, and there's forces from the mountain. I see a few questions in the chat on the previous problem. I'll come back to them at the end of the class and try and answer them then if they don't get answered in the chat right now. So if that rock is in equilibrium, rotational translational equilibrium, there are forces acting on that rock, gravity, the mountain, but it must be those forces add up to 0. If they add up to 0, the forces add up to 0, then there'll be no acceleration of the rock. And if it's at rest, it will stay at rest. Likewise, there are torques acting on that rock that will tend to try and rotate the rock, turn the rock. But if it's at rest and staying at rest, those torques must also add up to 0 so that there's no angular acceleration of the rock. It doesn't start turning. And that's rotational equilibrium. And so equilibrium of rigid bodies means 2 things. That the sum of the forces add up to 0, which won't change the translational motion because there's no acceleration. The sum of the torques add up to 0. There won't be any angular acceleration. There'll be no change in rotational motion. And that's what we mean by equilibrium for rigid bodies. Okay, so as an example of equilibrium, I want to work through in the last 10 minutes this problem. And it's probably going to take me these 10 minutes. So in the picture, there's a gymnast on a beam. And we're told that some things about the gymnast on the beam. So it's a little hard to see the picture, but I'll start annotating it. This is the beam, and the length of the beam is 5 meters. we're told that the beam is supported by two uprights. There's one over here on the left and one over here on the right. And we're told that the beam's mass is 10 kilograms and that the gymnast's mass is, here's the gymnast applying a force, 50 kilograms. And we're told that the gymnast is 1 meter from the right upright. So it doesn't quite look like it in this picture, but let's take the question at face value. We're told that this distance from the right upright, here's the right, here's the left, that's 1 meter. And given all that information, so we know the mass of the beam, we know the mass of the gymnast, we know how the arrangement by which the beam and the gymnast is supported. We got to figure out the force, the upward force that the left and right uprights are exerting. So what's this force over here? What's this force over here? I'll call them F left and F right. And we're going to do this by our understanding of rigid bodies, center of mass, and rotational equilibrium. So it's really collecting together these individual topics that we've discussed today about torques, about center of mass, and about equilibrium. Okay, so of course, I wouldn't do anything else. I want to draw a picture. I want to draw a sketch of the forces that are acting on the beam. And so let me make it clear about this picture. I'm going to focus on the beam and the forces that are acting on the beam. And that's going to lead me to figuring out the force acting from the left-hand support on the beam and the force acting from the right-hand support on the beam. I'm really just focusing on the beam and what forces acting what forces are acting on the beam. Obviously, the beam is exerting forces on the gymnast and on the earth and on the left and right supports, but I'm not going to worry about all of that. Okay, so in this turquoise, I don't know what color this is the beam running horizontally. Over here on the okay, so I've actually made the gymnast 1 meter from the left-hand end of the support rather than the right-hand end of the support. I realize that, but it's, you know, I just walked around the other side of the gymnast. That's okay. Forgive me. So here's the gymnast on the beam. And then here's the left-hand support. And here's the right-hand support in green and in blue. And so there's four forces that are acting on the beam. There's the force of gravity due to the gymnast being supported by the beam. As I call that W1, the force of the gravity on the beam itself, and the force from the left-hand support and the force from the right-hand support. I call those F left and FR. And I know a bunch of things about these forces. So I know that the weight of the beam is 98 newtons. Its mass was 10 kilograms. And I know the weight of the gymnast is 490 newtons. Her mass was 50 kilograms. And so I know the strength of these forces, and I know that they're straight downwards. I also know the locations of these forces. The gymnast is standing on the beam 1 meter from this end, this left end. The weight of the beam acts at the geometric center because it's a symmetric beam. That's where the center of mass is, and that's where we think of the weight of the beam acting. So that's there at the center, 2.5 meters from either the left-hand side or the right-hand side. And so I know the strengths of those two forces of gravity and their locations. I know the locations of the forces from the supports, the uprights. So I know where FL acts and FR acts, but I don't know their sizes. And what we're going to do is apply equilibrium to find the size of the left-hand force and find the size of the right-hand force. Okay, so it's done in 2 steps. Solving this is done in 2 steps. First I'm going to apply rotational equilibrium. And then I'm going to apply translational equilibrium. And when I apply rotational equilibrium, I first found out this force from the right-hand support. And then when I did translational equilibrium, I'm going to find the force from the left-hand support. And so here my job is basically to find the force exerted by this right-hand support. I'm going to find this one here. And I'm going to do it by applying rotational equilibrium at the left-hand support. This beam is in equilibrium. It's not falling down. It's not flying into the air. So it's in equilibrium. And so the sum of the torques on the beam must be 0. And I'm going to work out the sum of the torques about where the left-hand force acts. Now, the key thing is that the left-hand force, since it acts at that axis of rotation, at that point, it itself creates no torque. So if I think of the torque about where the left-hand force acts, the left-hand force is producing no torque about that point. The only torques are created by the weight of the gymnast, the weight of the beam, and the force of the right-hand support. We know the strengths of 2 of those forces, but not the third. We know the locations of all 3 of those forces. They're at distances 1 meter, 2.5 meters, and 5 meters from the left-hand support. And so we've got all the ingredients to actually solve for the right-hand force. Let me show you how it works. I'm going to add up all the torques. Torque 1 is from the gymnast. Torque 2 is from the beam. Torque 3 is from the right-hand support. Torque R is from the right-hand support. The gymnast and the force of gravity on the beam are trying to turn it clockwise. I call that the negative direction. The right-hand support is trying to push it counterclockwise. That's the positive direction. I filled in the fact that those torques in general are distance from the axis of rotation times the force times the sine of the angle between the direction of the force and the direction of the displacement vector from the axis of rotation. In all of these 3 cases, these forces are at right angles to the line from the axis of rotation. So it's always sine of 90 degrees, which is 1. And so all we have to do is multiply force times distance, the gymnast's weight times the distance of the gymnast from the axis of rotation, the beam's weight, W2, times the distance from the axis of rotation, the force FR from the right-hand support times the distance from the axis of rotation. That's all I'm doing here, here, and here. If you look at this equation that I've made, that these 3 terms add up to 0, well, we don't know this force FR, but everything else in there we know. So I can just take the first 2 terms over to the right-hand side, divide by RR, the distance to where the force of the right-hand support is applied, and get this little equation here, and plug in all the values, the locations of the 3 forces and the size of the 2 weights. And if you get that, plug all that in, you find the force of the right-hand support. And so that's the force that's being exerted here. It's 147 newtons. So that was the hard bit. Now it gets easy. Once you know one of these 2 forces from the 2 supports, it's easy to use this. This should say, there's a mistake here. This should say translational. It's easy to use translational equilibrium to find this fourth force. Look, you got 490 newtons down, 98 newtons down, 147 newtons up. The size of SL upwards must be just the right size when combined with FR upwards to balance the total forces of gravity downwards. i.e., if I add the forces in the vertical direction, weight of the gymnast downwards, weight of the beam downwards, force of the right-hand support upwards, force of the left-hand support upwards, they must add up to 0. The only thing in this equation that I just built from translational equilibrium that I don't know is the force from the left-hand support. I can rearrange it as an equation for the force from the left-hand support. It's the sum of the weights less the help that is provided by the right-hand support. It's the sum of 490 newtons plus 98 newtons less the help that's provided by the right-hand support, 147 newtons. That left-hand support is exerting a force of 441 newtons. And so that's the answer for the left-hand support. You notice the left-hand support does more, exerts more force, the right-hand support less force in supporting the beam and the athlete. That's because the athlete is nearer the left. If the athlete walked along to be nearer the right, then the roles would reverse and the right hand would support more, the left hand would be less. The athlete was dead center. They'd support the athlete by equal amounts. Anyway, let me end there. Sorry, I've overrun a minute or 2 minutes. We've worked through rotational equilibrium on our first lecture on rigid body dynamics as we go on to explore the world of rigid body motion. And so we'll continue that in next class.